Hello everyone, this is Paragi Joshi. In today's video, we are going to solve end semester examination question paper. So let us proceed. Question number one. Give notations of representation of the following components of formal languages. In this question, we have to represent the components of formal languages. The first component is alphabet. Alphabet is represented by sigma. The second component is string. String is represented by W or X. The third component is empty string. Empty string can be represented by epsilon naught or lambda. The fourth component is length of string. The length of string can be represented by W. The fifth component is prefix and suffix. Prefix and suffix can be represented by epsilon naught, T, TO, or TOC if the word is TOC. The sixth component is language. Language is represented by a capital L. The seventh component is operators on language. There are different operators in formal languages, and the operators are union, intersection, clean stars, and concatenation. Now let us proceed to the next question. Question number one, B part. Define FA. Acceptance of string by FA. What is FA? FA is known as finite automata. Finite automata is the simplest machine to recognize patterns. It is used to characterize a regular language. For example, VBA plus. Also, it is used to analyze and recognize natural languages expression. The finite automata or finite state machine is an abstract machine that has five elements or tuples. It has a set of states and rules for moving from one state to another, but it depends upon the applied symbols. Based on the states and the set of rules, the input string can be either accepted or rejected. Basically, it is an abstract model of a digital computer which reads an input string and changes its internal state depending on the current input symbol. The accepted strings by FA are Q, small q, capital F, sigma, and the transition symbol. Okay, let us proceed to the next part of the first question. Part C. Give four differences between NFA and DFA. NFA stands for non-deterministic finite automata, whereas DFA stands for deterministic finite automata. NFA can use empty string transition. DFA cannot use empty string transition. NFA is easier to construct, whereas DFA is not easy to construct. It is difficult to construct. NFA, no need to specify how does the NFA react according to some symbol. For each symbolic representation in DFA of the alphabet, there is only one transition state in DFA. Okay, so this question is done here. Let us proceed to the next question of question one. We have to state true or false. The first part is if L is a language accepted by NFA, then L is also accepted by DFA. Yes, it is a true statement. As we already know that L is a language. If it is accepted by NFA, then it will always be accepted by a DFA. The second part is for every NFA, there exists an equivalent DFA that stimulates the behavior of NFA. It is also true because for every NFA, there is a equivalent DFA that we can construct so that we can stimulate the behavior of NFA. The C part is in NFA to DFA conversion for N state NFA there exists at most two N state in DFA. This is not the correct statement because there exists 2 to the power N state in DFA where if there are N states in NFA. Okay, so the first question is over now. Let us proceed to question number 2. Question number 2, A part. What are regular set or regular languages? What are valid operation used in regular expression? So let us see what are regular set or regular languages. Regular languages are the most restricted type of languages that are accepted by finite automata. In Chomsky hierarchy, regular languages are the most restricted grammar that are accepted by finite automata. A language is regular if it can be expressed in terms of regular expressions. Regular expressions are used to denote regular languages. A language L is a regular language if there exists a finite automata to it that decides the language. If regular language exists, there should exist a finite automata according to the regular language. Since a language L is a set of strings, one way to make new language is to use standard set operations such as union, intersection, and make new strings. The valid operation used in regular expressions are union, that is L1 union L2, intersection, that is L1 intersection L2, concatenation, that is L1 plus L2, clean star, that is L1 star, complement, that is L complement G. Now let us proceed to the next part of question number 2. we have to complete the given table with the correct regular expression. So you can see there is also there is given regular expression to the corresponding regular languages in the table. If the language is 0, 1 or 1, 1, we know that the regular expression should be 0, 1 plus 1, 1. If the language is epsilon not 0, 0 or 0, 0, then it should be 0 star because the value of star can be from 0 to infinity. Set of all strings from A to B, length 3 or less. So the regular expression should be epsilon naught plus 0 plus 1 plus 0 plus 1 plus 0 plus 1 plus. If the regular expression is 0 to the power 2n, if n is greater than equal to 0, then there should be at least one 0 because it is in the power of 2 to the power n. So the regular expression corresponding to this language is 0, 0 star. Another language is 0 to the power 2n plus 1. Here we know that the power is 2n plus 1. So the regular expression corresponding to it is 0, 0, 0 star. And the last is even palindrome. The regular expression for even palindrome does not exist. Okay, so now let us proceed to the next part of question number B. Question number 2. Question number 2. Explain Arden's theorem. Arden's theorem states that if P and Q are two regular expressions over sigma and if P does not contain epsilon naught, then following the equation in R given by R is equals to Q plus RP has a unique solution. That is R is equals to QP star. That means whenever we get any equation in the form of R is equals to Q plus RP, then we can directly replace it with R is equals to QP. Here is the given proof of why we can replace R is equals to Q plus RP with R is equals to QP star. You can refer to the proof here. Okay, now let us proceed to the next part of question number 2. We have question number 3 here. Question number 3 states that define the grammar for the following languages, complete the table. In question number 3, we have to complete the table of all the given type of grammars, that is type 0, type 1, type 2 and type 3. Type 0 grammar, uh, type 0 grammar is the name of, in the name of the type 0 grammar is unrestricted and phase structured. The name of type 1 grammar is context sensitive grammar. The name of type 2 grammar is context free grammar, and the name of type 3 grammar is regular grammar. Now, the name of languages corresponding to the type are type 0 for recursive enumerable language, context sensitive language for type 1, context free language for type 2, and regular language for type 3. The name of recognized automata, that is the automata that is used to perform operations on these type of full grammars. The type 0 grammar requires Turing machine, type 1 grammar requires linear bounded automata, type 2 grammar requires push-down automata and type 3 requires finite automata. Popular examples are given here. You can see it on the screen. Now let us proceed to question number 4. In question number 4, we have to define the context-free language, complete the table with the appropriate production rule. We have to provide the production rules for the grammar, for the context-free language given in the left column. So let us see. The first language is 0 to the power n star and 1 to the power n. Here the corresponding production rule is S, where S 0 S1 and the terminal are 0 1. The next language is W star, W to the power R, where W belongs to 0, 1 star. W is reverse of every string in W. W is even palindrome. We can see that W is an even palindrome. So the grammar corresponding to it is 0 S0, 1 S1, and the terminals are 0, 0 and 1, 1, as it is require a even palindrome. The third language is WX star, W to the power R, where W belongs to 0, 1 star, and W to the power R is the reverse of W. In W, every string is an even palindrome with X as the middle character of the string. We know that X should be the middle character of the string. So the corresponding grammar to it is S is equals to 0 S0, 1 S1, and a hash string. The fourth language is W, in that belongs to 0, 1 star. W contains equal number of zeros and W contains equal number of ones. So the corresponding production rules are 0 S, 1 S, then 1 S, 0 S, and terminals are 0, 1 and 1, 0. As we know that it should contain equal number of zeros and equal number of ones. Now let us proceed to question number 5. Okay, now we have question number 6. Give two examples of each. First sub part is decision problem. The first part, the decision problems are the problems which can be found by giving a decision to the problem. So the type of decision problems are Q. First example is Q2. Is true or perfect square or not? We can have two decisions in this problem, that is yes or no. Is it two a perfect square or not? So the answer would be no. The second example is given two number x and y. Does x evenly divisible? Evenly divide y. Here also we have two decisions, that is yes or no. So x and y can be any two numbers. You can see the decision would be a yes or either no. Now, second part is optimization problem. The example of optimization problems are: find the path from 0 to v, u to v that uses the fewest edges. It is used for finding the shortest distance, that is Dijkstra's algorithm used in maps. The second is crew scheduling. It is also optimization problem. The third subpart is undecidability, whether a CFG generates all strings or not, whether two CFG L and M are equal. Here we don't have a decision on that, so we have to proceed with the solution and find the decision in the process. The fourth subpart is P and NP. P example of P problems are linear searching, matrix multiplication, and merge sort. The NP problems are traveling salesman problem, N cross N Sudoku, and Candy Crush problem. The fifth subpart is recursive language. Here the two types of language, example of two types of recursive language are given. So you can see. Okay, now let us proceed to question number 7. In question number 7, we have to explain the following. Chomsky hierarchy. According to Chomsky hierarchy, grammar is divided into four parts as follows. Type 0 is known as unrestricted grammar. Type 1 is also known as context sensitive grammar. Type 2 is known as context free grammar, and type 3 is known as regular grammar. In the figure, you can see how the Chomsky hierarchy works. Type 0 grammar, type 1, then type 2, and then type 3. The type 3 grammar is the subset of type 0, 1, and 2. Type 2 is the subset of 1 and 0. Type 1 is the subset of 0. And type 0 is the universal grammar. Type 0 is the most unrestricted grammar recognized by the Turing machine. Type 1 is the context sensitive grammar. Type 2 is the context free grammar. And type 3 is the most restricted grammar, that is known as regular grammar. It is accepted by finite automata. Let us proceed with the analysis of all these grammars. Type 0 grammar is also known as unrestricted grammar. Type 0 grammar include all the formal grammar. Type 0 grammar language are recognized by Turing machine. These languages are also known as recursive enumerable language. The language known as recursive enumerable language. Type 1 context sensitive grammar. Type 1 grammar generate context sensitive languages. The language generated by grammar is recognized by linear bounded automata. Type 2 context free grammar. Context free grammar generate context free languages. The language generated by grammar is recognized by push-down automata. Type 3. Regular grammar. Type 3 grammar generate regular languages. These languages are exactly all languages that can be accepted by a finite state automation. Type 3 is the most restricted form of the grammar. Okay, so we have covered all the type of grammar in the Chomsky hierarchy. Now let us proceed to the next part of question number 7. The next subpart is PDA, 2 PDA, and NPDA. We have to describe all of them. So, what is PDA? PDA is push down automata. Push down automata is a way to implement context free grammar. A context free grammar or context free language can be used according to push down automata. We design finite automata for regular grammar. Similarly, we have to design push down automata for context free grammar. It is more powerful than a finite state machine. Finite state machine has very limited memory, but PDA has more memory. PDA is equal to finite state machine plus 10. PDA requires a stack to work with now. So let us proceed to the next part, that is 2 PDA. Two-way non-deterministic pushdown automata. Our classical non-deterministic pushdown automata enhanced with the two-way motion of the input head. NPDA. The non-deterministic pushdown automata is very similar to NFA. In a NPDA, at a given configuration, the machine may have multiple choices for the next move. This contrasts with the deterministic pushdown automata, where there is only one possible transition for each configuration. The non-determinism in NPDA allows it to explore multiple possible computation paths simultaneously. If any of these paths leads to an accepting state, the input string is accepted by automation. Okay, now let us proceed to the last part of the question number 7. Recursive enumerable languages. What are recursive enumerable languages? Recursive enumerable languages type 0 languages are generated by type 0 grammar. Type 0 grammar is the most unrestricted type of grammar. A recursive language can be accepted or recognized by Turing machine, which means it will enter into final state for the strings of languages and may or may not enter into the rejecting state for the string which are not part of the language. It means Turing machine can loop forever for the string which are not part of the language. RE languages are also called Turing machine recognizable languages. A language L is recursive enumerable if L is the set of strings accepted by some Turing machine. If L is a recursive enumerable language, then if W belongs to L, then a Turing machine halts in the final state. If W does not belong to L, that is a string does not belong to L, then a Turing machine halts in the null final state or loop forever. This is how a recursive enumerable language works. Okay, now here we are at the end of this video. Thank you for watching.